p-values and dance of the p-values. Many people in research rely quite heavily on p-values. They have in the past regarded them as very important in their analysis. How do they think about them? Well, I think many of them think about P as a measure of strength of evidence against the null hypothesis, and that's a pretty sensible way to think about them. They probably think of the p-values in terms of sort of bands, like 3 stars up to 0.001, 2 stars less than 0.01, 1 star. Between 0.5 and 1.0, that sort of grey area, not quite statistically significant, or p greater than 0.1. And I can identify those bands oh, and so sad. And associated with those bands is language, highly significant through to non-significant. Does this bring to mind some red flag? And people tend to believe that this tells them about truth. 3 stars, yes, definitely an effect. No effect with p greater than 0.1, or perhaps the effect is 0. Does this bring to mind a couple of red flags? And there's emotion involved. People are delighted or terribly depressed depending on their p-values. And in the world, people make decisions based on these sorts of things. Okay, I'm being a bit flippant about it, but for many people, p-values are deeply entrenched in how they think about their data analysis and their research conclusions. And I think this is really a big problem, and the red flags point to some of the strong warnings and cautions we need to have whenever we come across p-values. But there's one more reason that I think is perhaps even stronger why p-values are deeply misleading and estimation is much more informative. I'm going to switch to dance of the p-values here. I'm going to discuss how unreliable, how misleading p-values can be. So let's take a typical experiment. I'm assuming we've got a control population and an experimental population, and that the true difference between the two population means is 10 points on this scale. You could think of this, say, as a well-being scale. The experimental group might be folks from your college. Folks at no-name college down the road, of course, have on average a lower well-being. They're the control population. Now we want to run a study with 2 groups, each of 32 independent groups. In our first experiment, we found these 32 data points, and there's the mean and 95% confidence interval for the control condition, students from no-name college. Whereas from your college, here we have the experimental, the 32 ratings of well-being, and the mean and confidence interval. Let's turn on the difference axis because we're estimating the difference between these populations, and this experiment happened to estimate about 9.5 points. If we run it again, we drop down that first mean and confidence interval, and here's the second one, just a whisker less, about 9. Do it again, and we happen to estimate around about 3 points. And we can run this down, and there is the dance of the confidence intervals, exactly as we'd expect. We can turn on the true difference because we're in the computer and we know that at 10 points. And we can colour confidence intervals that don't include this true value red, and we happen to just have 1 in red there. And I can run this dance, and in the long term we'll find that 5% of these intervals are red and 95% are green because they capture. Fascinating to watch. In the short term we might get no red for a while, and then we might get a clump of several of them. Randomness is very lumpy in the short term, very unpredictable. There's a whole clump. But in the long term, we'll get exactly 95% capturing and 5% that are red. So that's all exactly as you expect. Now let's consider p-values. And I'll run an experiment. And this experiment happened to estimate about 15, and there is our mean and confidence interval. Here is 0 lined up with a control sample mean and our difference axis. This result is well clear of the null hypothesized value, so we know our p-value would be small, and in fact it's 0.003. Let's do another one. Oh, the deep down sound of p greater than 0.1, because this confidence interval easily overlaps the null hypothesized value. P is around about 0.5. Or another one overlapping. And that is the dance of the confidence intervals, exactly as we expect, but now the dance of the p-values. In each case, we can translate across using our eyeballing from a particular confidence interval to a particular p-value. But now look at these p-values. They range from 3 stars up to 0.649, 3 stars, 2 stars, question mark, and up to 0.478. It looks like just about any value at all is possible, and we can display that a little differently here. So over here we have the dance of the p-values, and you can make up the song or dance it yourself to your own design as you wish. Now, I think many people who use p-values do not fully deeply appreciate just how incredibly variable, how incredibly unreliable p-values are. Here's another way to look at it. Let's clear this and hide the population and run a single experiment. There it is. Now, this is all an experimenter actually knows. Our data and our calculated means, confidence interval, and p-value. That's all we have. And we have to imagine that there are populations underlying this and imagine the dance. Of course, our result is one chosen randomly from a dance. If I tell you just this confidence interval here, does that give you any information about the dance of the confidence intervals? Yes, it does, because the length of this interval gives you a pretty good idea about the amount of bouncing around in the dance of the confidence intervals. It doesn't tell you exactly where that dance will be, but it indicates the uncertainty in our result. Whereas if I give you only the p-value, or the p-value and the mean, then you get virtually no information about what p-value is likely on the next experiment. No information about the dance of the p-values. The trouble is that a single p-value tempts us to think that we have some degree of certainty. It does not signal the extent of great uncertainty that we actually have, the likely enormous difference between our p-value and later ones in the dance. And that's one way of describing how the confidence interval, how estimation, is much more informative than p-values. Once you've got the mean and confidence interval, the p-value adds nothing. If you want the p-value, you can calculate it or eyeball it. But the confidence interval indicates clearly, it puts it in our face, how great the uncertainty is. That might make us a bit disappointed, but at least it's true, it's accurate. There is that amount of uncertainty in our data. And it's important that we appreciate that. It might drive us to design a better experiment next time. It might drive us to look for other studies we can combine via meta-analysis to produce a more precise estimate. And those are very valuable things to be aiming for. So my conclusion is that we can't really trust p-values. We shouldn't rely on them. They bounce around with replication. Confidence intervals bounce around with replication too, but each interval signals the degree of uncertainty, and it's very important that we appreciate that. So confidence intervals, estimation, meta-analysis are very informative, and that's what should be our choice. I should mention that this Dance of the p-values page of ESCI is not part of ESCI Intro. I'm afraid it only works in old versions of Excel. So, our red flag number 5, dance with the p-values. Beware the unreliability of p-values. Prefer estimation.